Hello, night travelers. Welcome back to the Night Observer, a quiet place for souls seeking calm, where we gather to listen to the eternal symphony of the universe. Find a comfortable position on your soft bed. Let your shoulders gently loosen, and feel a slow warmth spreading from your chest to your fingertips. In my thoughts, I have lit a small fire once more. We gather around it again tonight, allowing its glow to steady us as we listen to stories of the most wondrous things that exist. As the noise of the daytime world slowly dissolves into silence, I invite you to travel with me inward, toward the very core of reality itself. Tonight, we will not begin with vast galaxies or blazing stars. Instead, we will shrink our perspective millions of times over, descending into the strange and delicate realm of quantum physics. Let your breathing become light and even. Listen carefully, and you may begin to hear a quiet love song, the song of tiny particles weaving the fabric of the entire universe. Welcome to the chapter, Prelude, the world of the unimaginable. This is the threshold of our journey down the famous rabbit hole of quantum physics, where we explore the hidden threads that hold reality together. A vision through the microscope of the mind. Dear night travelers, to glimpse this world, we must adopt an entirely new way of seeing. Imagine you are holding a soccer ball in your hands. In your mind, allow that ball to grow larger and larger, until it expands to the size of the entire Earth. Only when it becomes as vast as the planet itself do the tiny details come into view. Those details are atoms, the fundamental inhabitants of matter. Quantum physics is the science devoted to studying these tiny residents, along with light and other subatomic particles. It is not some distant or abstract branch of science. In truth, it is the foundation beneath everything around us, from the way stars shine to the quiet operation of the device resting beside your bed. The difference between atom and quantum. These two words are often confused, so tonight, by our mental campfire, let us gently separate them. Atoms are entities. They are the physical building blocks of matter, structures that possess form and occupy space, even if their boundaries are somewhat indistinct. A quantum, however, is not a thing. It is a unit. The word quantum comes from Latin, meaning how much. In physics, it refers to the smallest possible amount of any physical quantity involved in an interaction. Energy, it turns out, does not flow smoothly like an unbroken stream of water. Instead, it moves in tiny, indivisible packets. A photon, for example, is a quantum of light. You cannot divide it in half. It either exists or it does not. In this way, atoms are the actors on the stage, while quanta are the smallest steps, the minimal exchanges of energy that allow those actors to interact. The collapse of the clock universe. Breathe slowly, deeply. Before quantum physics emerged, humanity believed it lived inside what we now call a Newtonian universe, a perfectly ordered cosmic clock. In that world, if you knew an object's position and speed, you could predict its future forever. Cause and effect appeared absolute. A thrown stone followed a precise path. Water always flowed downward. Certainty reigned. But just over a century ago, when scientists began to peer more deeply into the structure of matter, that certainty quietly dissolved. At the smallest scales, reality no longer behaved like clockwork. Instead, it revealed itself as a realm of probabilities, the world of the unbelievable. Why do we call this the world of the unimaginable? Because here, particles behave in ways that defy every instinct shaped by everyday life. Superposition. An electron does not occupy a single position when unobserved. Instead, it exists in a blurred state, a combination of many possibilities at once. Only when it is observed does it settle into one definite outcome. Wave-particle duality. Objects we imagine as solid particles can behave like spreading waves. At the same time, light, once thought to be purely a wave, arrives in discrete packets. The famous double-slit experiment revealed that even a single electron can pass through two openings simultaneously and interfere with itself. Uncertainty. Werner Heisenberg showed that there is a fundamental limit to knowledge itself. One cannot precisely know both the position and the velocity of a particle at the same time. The more clearly one is known, the more the other dissolves into uncertainty. Night travelers, we begin to see that solidity itself is an illusion, constructed from probabilities, motion, and tiny parcels of energy. The quantum world may seem strange, even unsettling. Yet it teaches us that reality is far richer and deeper than what our eyes alone can perceive. Tonight, there is no need to wrestle with equations. Simply allow your thoughts to drift, light as a cloud of probability suspended in the void. Feel now the quiet safety of Earth beneath you. You are, in essence, awakened stardust, formed from atoms forged in the hearts of ancient stars, governed by these subtle quantum laws. Concerns of tomorrow and echoes of yesterday fade gently into the vast stillness of space. An epic of a new perspective, a history of discovery. Take a slow breath. Fill your lungs with calm and release it gently as our story turns back in time. The greatest scientific revolution did not begin with colossal machines or cosmic explosions. It began with a simple, practical problem: light. In Berlin during the 1890s, engineers struggled to understand why heated filaments in light bulbs changed color. Classical physics predicted that hotter objects should glow increasingly blue and emit infinite ultraviolet radiation. But reality refused to cooperate. Instead, the light remained soft, pink, white, and warm. This contradiction became known as the ultraviolet catastrophe, a complete failure of established theory. In 1900, a quiet and methodical physicist named Max Planck was asked to solve this puzzle. Working with blackbody radiation experiments, he arrived at an astonishing conclusion. Energy, he realized, was not emitted continuously, but in discrete packets. On December 14, 1900, Planck introduced the concept of the quantum and unveiled what we now call Planck's constant, the bridge between energy and frequency. Yet even then, Planck believed this was merely a mathematical convenience, not a reflection of reality itself. He did not know that in that moment, he had opened a door leading into a deep and endless rabbit hole, one that humanity is still exploring today. Einstein and the moment quantum theory became real. Dear traveler, let your breathing soften, slow and steady. 5 years after Max Planck quietly introduced what he believed was only a mathematical trick, a young and largely unknown clerk working at a patent office in Bern, Switzerland, dared to take that idea seriously. His name was Albert Einstein. In the almost mythical year of 1905, Einstein applied Planck's quantum hypothesis to explain a puzzling phenomenon known as the photoelectric effect, the emission of electrons from a metal surface when light strikes it. Scientists before him were deeply confused. Powerful red light, no matter how intense, could not dislodge a single electron. Yet faint violet light caused electrons to leap out instantly. Classical wave theory offered no explanation. Einstein proposed an idea that, at the time, sounded almost sacrilegious. Forget light as a smooth wave. Instead, imagine it as a stream of tiny packets of energy, photons. Each photon carries a fixed amount of energy. Red photons carry too little to make an impact, while ultraviolet photons strike like heavier projectiles, strong enough to knock electrons free. With this simple and elegant insight, Einstein transformed the quantum from an abstract number into something physically real. This was the moment modern physics truly began, the moment we accepted that light carries a dual nature, both wave and particle. Einstein would later receive the Nobel Prize for this work, honoring the courage it took to see clarity where others saw impossibility. Niels Bohr, and the architecture of the atom. Once light itself had been quantized, a deeper question naturally followed. Could matter also be governed by these same rules? One of the most imaginative answers came from the Danish physicist Niels Bohr, a man known for debating science with the same enthusiasm he brought to a game of table tennis. In 1913, Bohr proposed a radical model of the atom. Electrons, he suggested, do not wander freely around the nucleus. Instead, they are confined to specific allowed orbits, like planets bound to invisible tracks. When an electron absorbs energy, it does not slide smoothly outward. It jumps, instantly, from one orbit to another. And when it falls back, it releases that energy as a photon of a precise wavelength. There is no path between, no gradual motion, only disappearance and reappearance. Bohr called this a quantum leap. This strange idea explained why each chemical element emits its own distinctive bands of light, unique spectral fingerprints written into the cosmos. Though it defied every classical intuition about motion, experiment after experiment confirmed its accuracy. At the smallest scales, nature obeyed quantum law, and nothing else. The explosion of the 1920s, waves and uncertainty. Night travelers, allow your eyelids to grow heavy as we enter the most luminous chapter of this story. By the mid-1920s, quantum theory ceased to be a collection of isolated insights. It became a complete and unified framework. In 1923, the French physicist Louis de Broglie offered a stunning reversal of perspective. If light could behave like a particle, he asked, why should particles not behave like waves? Even electrons, he proposed, possess wave-like properties. This idea inspired Erwin Schrödinger to develop wave mechanics in 1925. His now famous equation did not describe electrons as tiny solid dots, but as shimmering clouds of possibility, mathematical waves encoding where a particle might be found. At the same time, in Germany, Werner Heisenberg approached the problem from an entirely different direction. Using matrix mathematics, he uncovered a profound limit built into nature itself, the uncertainty principle. You can never know both the exact position and the exact motion of a particle at the same time. The more precisely one is known, the more the other dissolves into uncertainty. At this level, reality is not a sharp photograph, but a softly shifting mist. Then, in 1926, Max Born provided the final key. Schrödinger's wave, he explained, does not describe a blurred object. It describes probability itself. The height of the wave tells us where a particle is most likely to appear. With that insight, the clockwork universe of Newton finally gave way to a cosmos ruled by chance, probability, and possibility. Solvay, 1927, When Giants Met. All of these ideas converged in a single historic gathering, the Fifth Solvay Conference in Brussels, 1927. Imagine the room: Einstein, Marie Curie, Planck, Bohr, Heisenberg, Schrödinger, Pauli, many of the greatest minds humanity has ever produced, all grappling with the same unsettling realization. Quantum physics was no longer a curiosity. It was accepted, and with it came a radical truth. The foundations of reality itself were nothing like what we had imagined. In this new world, particles could exist in multiple states at once. Reality did not fully crystallize until it was observed. What we call real was built upon entities that defied all classical notions of reality, Paul Dirac and the bridge to the future. As the decade drew to a close, one final figure completed the framework. Quiet, reserved, and profoundly precise, Paul Dirac unified quantum theory with Einstein's special relativity in 1928. The Dirac equation not only explained the intrinsic spin of the electron, it made a breathtaking prediction. For every particle, Dirac reasoned, there must exist a counterpart with opposite charge. Antimatter. In 1932, the positron, the electron's mirror image, was discovered, confirming Dirac's vision and revealing the extraordinary predictive power of quantum mathematics. From this work emerged quantum field theory, our deepest description of how particles arise, interact, and vanish throughout the universe. You have now followed the paths of extraordinary minds, from Planck to Einstein, from Bohr to Heisenberg, from Schrödinger to Dirac, each helping to chart the smallest regions of existence, yet revealing laws that govern everything. Now, let these thoughts gently fade. Let quantum leaps and probability waves dissolve into the soft haze of sleep. You do not need to grasp their strangeness tonight. Simply rest, knowing that the universe spent 13.8 billion years preparing the conditions for this moment, so that you could lie here, safe, cradled by the quiet and subtle laws of the quantum world. When particles are no longer marbles, the strange difference. Let us move gently forward into a quieter and deeper chapter, when particles are no longer marbles. This is a journey down the familiar rabbit hole of quantum physics, where reality reveals itself not as solid stone, but as a delicate and ever-shifting dance of possibility. Prelude: the collapse of the clockwork universe. For centuries, humanity lived comfortably within the framework of Isaac Newton's classical physics. It was a deterministic clockwork universe, precise, orderly, and predictable. If you knew the exact position of a ball, its speed, and the forces acting upon it, you could calculate where it would be in 10 seconds, or in 10 years. In that world, objects possessed definite positions. They moved along clear trajectories. They existed in one place at one time, and nowhere else. But roughly a century ago, as scientists peered deeper into the heart of matter, down to the scale of atoms, that comforting certainty quietly dissolved. The fundamental building blocks of reality, electrons and photons, refused to behave like tiny billiard balls. They would not remain fixed in one position, nor obey the logic shaped by our everyday experience. The double-slit experiment, where logic begins to fray. To understand this unsettling difference, we must turn to one of the most famous and perplexing experiments in the history of science, the double-slit experiment. Imagine a device that fires small marbles toward a barrier with two narrow parallel slits. Behind it stands a screen to record where the marbles land. Common sense tells us exactly what should happen. Marbles passing through the left slit form a line on the left. Those passing through the right slit form a line on the right. Two slits, two lines. And that is precisely what happens until the marbles are replaced with electrons. Instead of two simple bands, the screen reveals an interference pattern, alternating bright and dark stripes. This is the unmistakable signature of waves, like ripples on water overlapping, peaks reinforcing one another, troughs canceling each other out. Somehow, particles are behaving like waves. The mystery deepens further. Scientists reduce the experiment to its quietest extreme, firing electrons one at a time. Each electron travels alone. There are no others to interact with. Yet, after thousands of electrons have struck the screen, the same interference pattern emerges. The question becomes unavoidable. What did each electron interfere with? Quantum theory offers a single, unsettling answer. It interfered with itself. In some profoundly counterintuitive way, a single particle appears to pass through both slits at once, existing in two places simultaneously, until it finally reveals itself upon the screen. Quantum superposition, a world of possibilities. Take a slow breath, in and out. This strange condition, where a particle exists in multiple states or locations at the same time, is known as quantum superposition. To imagine it, picture a coin spinning on a table. While it spins, it is neither fully heads nor fully tails. It is a blur containing both possibilities. In the quantum realm, an electron behaves in a similar way. Until it is observed, it does not occupy one definite position. Instead, it exists as a cloud of potential outcomes. Physicist Max Born showed that a particle cannot be described as a solid point, but only as a wave of probability. Where the wave rises highest, that is where the particle is most likely to appear when measured. The truly remarkable detail is this. The act of observation itself forces the particle to choose. Place a detector at the slits to observe which path the electron takes, and the interference pattern vanishes. The electron suddenly behaves like an ordinary particle again, obedient and localized. Niels Bohr concluded that at the deepest level, reality itself is indeterminate. There is no hidden, definite world waiting behind the curtain, only probabilities, until observation pulls one possibility into existence. This idea deeply troubled Albert Einstein. He famously objected that the moon must surely exist even when no one is looking at it, and he spent much of his life resisting the randomness at the heart of quantum theory. The uncertainty principle, the boundary of knowing. Dear traveler, the quantum world not only allows particles to exist in many states, it also places firm limits on what can ever be known. In classical physics, you can know everything about a moving car, its exact position and its speed. But Werner Heisenberg revealed that, at the quantum level, nature itself forbids such certainty. You can never know both the precise position and the precise momentum of a particle at the same time. The more accurately you determine where it is, the less you can know about where it is going. And if you measure its motion precisely, its position becomes blurred. This limitation does not arise from imperfect instruments. It is woven into the fabric of reality. At the smallest scales, the universe is inherently uncertain. This uncertainty extends even to energy and time. Over extremely brief intervals, energy can fluctuate dramatically, allowing phenomena such as quantum tunneling, where particles pass through barriers they seemingly should not cross. It is this subtle uncertainty that allows protons in the sun's core to overcome their mutual repulsion and fuse, releasing the energy that warms our planet and sustains life itself. You have seen how these tiny, elusive entities, through their quiet quantum dance, have shaped the vast and luminous universe around us. Quantum mechanics gently reminds us that reality is far richer, deeper, and more mysterious than what the naked eye can perceive. Tonight, there is no need to wrestle with equations or paradoxes. Let your thoughts soften. Let your mind become as light as a cloud of probability, drifting silently through the void, toward the invisible thread. In the next chapter, we will turn our full attention to a remarkable presence, an invisible thread that connects distant things while hiding itself in profound silence. Quantum entanglement, the mysterious linking thread of the universe. For now, allow your body to relax completely. Feel its weight sink into the bed. Draw a calm breath into your chest and release it slowly, letting go of the day's burdens. Let these words flow like a gentle current of light, carrying your awareness deeper toward the hidden structure that quietly binds all of reality together. Prelude, the symphony of connection. Dear traveler, in our everyday world, separation feels absolute. You are here, and I am there. To touch you, I must cross the space between us. For a radio signal to reach Mars, minutes must pass as it travels across the void. This is the law of classical physics, a universe governed by distance, sequence, and clear cause and effect. But when we shrink our gaze to the realm of atoms, millions of times smaller than a grain of sand, this certainty dissolves. There, we encounter a phenomenon so profound that space itself seems to lose its meaning. This is quantum entanglement. Imagine a remarkable source that creates pairs of particles, perhaps particles of light, photons. These pairs are born together, sharing a single quantum state so deeply that they cannot be described as independent objects. Even when separated by vast distances, they remain parts of one unified whole. Their fates are intertwined from the moment of their creation. And from this silent bond, a new understanding of connection begins to emerge. the phantom effect, and Einstein's resistance. This story of perplexity did not begin as an acceptance, but as an attempt at refutation. At the dawn of the 20th century, the world's greatest physicists gathered in Brussels, drawn together by a new theory that was quietly undermining the very foundations of reality. At the Solvay Conference of 1927, an intense intellectual confrontation unfolded. On one side stood Niels Bohr, who believed that reality itself remained vague and undefined until the moment it was observed. On the other stood Albert Einstein, the steadfast voice of reason, who could never accept a universe governed by chance. Einstein famously declared, "God does not play dice with the universe." He believed that the moon existed whether or not anyone looked at it. He believed in locality, the principle that an event here cannot instantaneously influence an event there without something physically traveling between them. In 1935, while working at the Institute for Advanced Study in Princeton, Einstein joined forces with two colleagues, Nathan Rosen and Boris Podolsky. Together, they published what would become a landmark paper, now known simply as the EPR paper. They were convinced they had uncovered a fatal flaw in quantum theory. Their argument was straightforward and deeply unsettling. If quantum mechanics were correct, then two particles, separated by unimaginable distances, one in Princeton and the other in the Andromeda Galaxy, could somehow influence each other instantly. Einstein dismissed this possibility with thinly veiled disdain, calling it spooky action at a distance. To him, such behavior was absurd, as it violated the cosmic speed limit imposed by his own theory of relativity. He proposed a more intuitive explanation. The particles, he suggested, were like a pair of gloves. Place one glove in a box and send it to Antarctica. Place the other in a box and send it to New York. When you open the box in New York and find a left glove, you immediately know the glove in Antarctica must be the right one. No message has traveled between them. The information was already determined from the start. Einstein believed subatomic particles worked the same way. They carried hidden properties, hidden variables, that quantum mechanics had not yet discovered. In his view, the theory was incomplete, not mysterious. John Bell and the game of absolute numbers. Let your breathing slow, steady, like the quiet ticking of time itself. For nearly 3 decades, the debate between Einstein and Bohr remained largely philosophical. It was often dismissed as untestable, even irrelevant. The world, after all, was focused on calculation, on building atomic bombs, transistors, and lasers. Few believed the argument could ever leave the realm of thought. Then, in 1964, a physicist from Northern Ireland named John Bell quietly changed everything. Bell was an independent thinker, unafraid to challenge assumptions. He realized that Einstein's objections could be translated into mathematics and tested in the real world. Bell derived a precise equation, now known as Bell's inequality. At its heart, Bell's idea was simple. If Einstein was correct, and particles carried predetermined properties like gloves in boxes, then their measured correlations could never exceed a certain numerical limit. But if Bohr was right, if particles were truly entangled, those correlations could surpass that limit. Bell transformed a philosophical disagreement into a scientific wager. If experiments violated his inequality, then Einstein's comforting intuition would fail, and spooky action would be undeniably real. Footsteps in the darkness, from Clauser to aspect. Let your eyelids grow heavy, and allow your thoughts to drift to Berkeley in the early 1970s. There, a young graduate student named John Clauser encountered Bell's paper and was immediately captivated. With little funding and much improvisation, Clauser assembled experimental equipment from discarded laboratory parts, determined to test Bell's inequality for the first time. When the results emerged, Clauser was stunned. He had hoped to vindicate Einstein. Instead, the data suggested the opposite. The particles were behaving as if they were deeply and mysteriously connected. Still, doubts remained. Critics argued that the particles might have found subtle ways to exchange information through ordinary means. The final turning point came in 1982 in Paris. There, the physicist Alain Aspect designed a far more refined experiment. His apparatus changed measurement settings while the particles were already in flight, so quickly that no signal, not even light, could possibly travel between them in time. The results were decisive. Bell's inequality was clearly violated. The strange connection Einstein had rejected was no longer a theoretical curiosity. It was a fact of nature. Anton Zeilinger and the halo of the future. As night deepens, let your imagination rise toward the Canary Islands, where physicist Anton Zeilinger aimed his telescopes at the sky. Zeilinger did not merely test quantum entanglement, he learned how to use it. His experiments demonstrated quantum teleportation, the transfer of a particle's quantum state to another particle many miles away, without the particle itself traveling through space. To eliminate every possible doubt, Zeilinger and physicist David Kaiser went even further. In the cosmic bell experiment, they used light from distant quasars, light that had begun its journey billions of years before Earth even existed, to determine measurement settings. No hidden conspiracy, no shared past, could influence the outcome. The conclusion was inescapable. Entanglement is real. The universe appears to be stitched together by invisible quantum threads. Why entanglement matters. You may wonder why humanity has spent decades pursuing such strange and elusive ideas. The answer is simple. They are reshaping the world you live in. Quantum entanglement is the foundation of quantum computing, where information is no longer limited to simple zeros and ones, but exists in interconnected superpositions capable of solving problems that would take classical computers thousands of years. It underpins the vision of a quantum internet where communication is fundamentally secure. Any attempt at eavesdropping would instantly reveal itself. But beyond all practical applications lies a deeper revelation. Entanglement hints at a universe far stranger than we ever imagined. Some physicists, including Juan Maldacena and Leonard Susskind, have proposed a breathtaking idea: the holographic universe. Perhaps space and time themselves are not fundamental. Perhaps they emerge from vast networks of entangled particles. The distance between Earth and Andromeda may not be a true separation at all, only an illusion shaped by how quantum information is woven together. As you rest here tonight, let that thought drift gently through your mind. The universe may be far more connected than it appears, and so perhaps are you. Night travelers. Tonight we will shrink our vision down 1,000,000 times to answer a question that has quietly reshaped the course of human history. Why is quantum physics so important? Let your breath become light and even, and begin to listen to the gentle love song of tiny particles weaving the fabric of this entire universe, the silent ruler of the visible world. Dear night travelers, we often imagine quantum physics as a distant outpost, an abstract discipline reserved for brilliant minds working behind the walls of advanced laboratories. Yet the truth is far more intimate. Quantum physics is not distant at all. It is the silent ruler behind everything you touch, everything you see, everything you feel each day. Without quantum laws, the world around you would simply not exist in its familiar form. Consider the stability of matter itself. According to classical physics, negatively charged electrons circling a positively charged nucleus should lose energy and collapse inward almost instantly. And yet, here you are. The bed beneath you remains solid. The walls stand firm. This stability exists because of quantization. Electrons are permitted to occupy only certain discrete energy levels, no more, no less. This quiet rule prevents atoms from collapsing, preserves the structure of matter, and allows life to emerge and endure. Quantum physics does not merely explain reality. It protects it from microscopic self-destruction. From the steam engine to the digital age. Breathe slowly, deeply. Imagine for a moment that quantum physics decided to fall silent. In an instant, modern civilization would dissolve. We would be carried backward to the 19th century, an age of steam engines, mechanical gears, and flickering telegraph wires. By understanding the motion of particles at the quantum level, humanity learned how to create the transistor, the fundamental cell of every electronic device. Every computer, every smartphone, every digital camera owes its existence to quantum mechanics. Engineers used quantum equations to design microscopic switches that guide the flow of electrons, forming the nervous system of the digital world. We are not merely studying quantum physics. We are living within a true quantum age, the chorus of light and the mirrors of time. Dear traveler, let your thoughts drift to one of humanity's most elegant creations, the laser. Compare it to the glow of an ordinary light bulb. A bulb emits light like a restless crowd, voices scattered, directions confused. A laser, by contrast, is a perfect symphony. Trillions of photons moving together, sharing the same rhythm, the same pitch, the same direction. This remarkable harmony arises from stimulated emission, a quantum insight first recognized by Einstein in 1917. Today, lasers quietly shape our lives, from delicate eye surgeries and supermarket scanners to the fiber optic cables carrying information across the planet. Even more astonishing, lasers allow us to measure the nearly immeasurable. Using ultra-stable laser beams, the LIGO Observatory detected gravitational waves, faint ripples in space-time produced by black holes colliding billions of years ago. Quantum physics has given humanity new eyes, capable of seeing into the deepest mysteries of the cosmos. The beat of eternity and the map in your hand. Now allow your body to soften and consider how we keep time itself. Every passing second is defined not by the turning of the Earth, but by a quantum heartbeat. Atomic clocks measure the precise vibrations of atoms, such as cesium or strontium, as they shift between quantum energy states. Their accuracy is profound. A strontium clock will lose or gain only 1 second over billions of years. The entire GPS system guiding you through streets and skies depends on the flawless synchronization of these clocks aboard satellites. Without quantum physics, and without accounting for relativity and quantum states, your navigation would drift into error within minutes. Quantum mechanics is humanity's most faithful timekeeper. Hope from the darkness, life and chemistry. Your eyelids grow heavier now. Let us turn to another quiet miracle, the chemical bond. The sciences of chemistry and biology are, at their core, written in the language of quantum physics. Every molecule, including the DNA that carries the blueprint of life, forms through the delicate interaction of electrons governed by quantum rules. These laws explain how atoms bind, how cells are built, and how complexity arises from simplicity. Even the human senses may whisper of quantum influence. The way we detect certain scents, or how migratory birds navigate using Earth's magnetic field, is suspected to involve phenomena such as quantum tunneling and entanglement within living systems. Quantum physics is not only the foundation of matter, it may be a key to understanding life itself, the dawn of quantum computing and the road ahead. As the night deepens, let your thoughts drift gently toward the future. There, new machines are quietly taking shape, quantum computers. Unlike conventional computers, which process information as simple zeros and ones, quantum computers operate with qubits. Through superposition and entanglement, qubits explore many possibilities at once. These machines promise breakthroughs once thought unreachable, discovering new medicines, optimizing global energy systems, and probing questions that lie at the edge of human understanding. We stand at the threshold of a profound technological transformation, one born from the same subtle laws governing atoms and stars alike. Echoes from the birth of the universe. Take a deep breath. Did you know that the immense structure of the universe, galaxies, clusters, and vast cosmic webs, began as tiny quantum whispers. In the earliest moments after the Big Bang, minuscule quantum fluctuations were stretched by rapid cosmic expansion. Over time, gravity amplified these faint irregularities, shaping them into stars and galaxies. Quantum physics also reveals that even black holes are not eternal, slowly releasing energy through Hawking radiation. The universe itself was written in the language of quantum mechanics from its very first moment. You have seen how tiny particles, through their silent dance, have woven together this vast and magnificent reality. You have glimpsed how small we are, and yet how far the human mind can reach. Now let thoughts of probability waves, of strange particles and distant black holes, soften and fade into the gentle mist of a dream. Space is a vast home, and Earth is the warm room that shelters you tonight. Everything continues its timeless rhythm, and so do you. Let your heartbeat fall into harmony with the quiet symphony of the stars. We will not merely speak of abstract ideas tonight. Instead, we will trace how these tiny particles have quietly woven modern life together, and how they have opened windows toward distant galaxies in this chapter. Quantum applications, from your pocket to distant galaxies. The silent ruler in your pocket. Dear night travelers, let us begin with what is closest to you now. The smartphone resting beside you, or perhaps still warm in your pocket. Have you ever paused to wonder how such a small object can hold such immense power, connecting you instantly to the wider world? At its core lies a humble yet extraordinary invention, the transistor. Built upon a deep understanding of how electrons behave at the quantum level, the transistor is the living cell of every modern electronic device. Without the laws of quantum physics governing the flow of electricity through semiconductors, humanity would still inhabit an age of steam engines and flickering telegraph wires. Every message you send, every image you watch, is the result of billions of tiny quantum switches turning on and off in perfect silence. The marvel does not stop there. The luminous screen before your eyes is another triumph of quantum mechanics, the light-emitting diode, or LED. Unlike an old filament bulb, an LED produces light when electrons make precise jumps between energy levels inside a crystal, releasing photons in the process. Even the flash memory that holds your photographs and memories depends on quantum tunneling, an effect that allows electrons to pass through barriers that classical physics deems impossible. Quantum physics is not distant or abstract. It rests quietly in the palm of your hand, faithful and unseen. A symphony of light and atomic pulse. Breathe slowly, deeply. Imagine stepping from your room into a modern clinic or a quiet supermarket aisle. There, you encounter one of humanity's most elegant tools, the laser. To understand its beauty, think of an incandescent light bulb as a restless crowd, voices scattered, directions confused. A laser, by contrast, is a disciplined choir, trillions of photons sharing the same color, the same rhythm, the same direction. This remarkable harmony arises from stimulated emission, a subtle quantum insight first recognized by Albert Einstein more than a century ago. Today, lasers serve us everywhere, from delicate eye surgeries that restore sight to barcode scanners that guide daily commerce. Even the fiber optic cables carrying the internet across oceans are guided pathways of laser light, moving information across continents with quiet precision. Now consider the GPS system guiding your travels. Each time you consult a map, you are relying on a quantum heartbeat. GPS satellites depend on atomic clocks of extraordinary accuracy. These clocks measure the vibrations of atoms, such as cesium or strontium, as electrons shift between quantum energy levels. Their precision is so remarkable that a strontium clock would drift by only 1 second over billions of years. Without quantum physics, these tiny timing errors would accumulate, and your navigation would become unreliable within minutes. quantum physics, the language of life and medicine. Dear traveler, allow your thoughts to turn inward, toward your own body. Chemistry and biology, at their deepest levels, are written in the language of quantum mechanics. Every molecule within you, including the elegant double helix of DNA, exists because electrons interact according to subtle quantum rules. Even the human sense of smell and the way migratory birds navigate using Earth's magnetic field are now believed to involve quantum effects, such as entanglement occurring within living cells. In medicine, quantum physics has given rise to what might be called gentle eyes. Technologies such as magnetic resonance imaging, MRI, and positron emission tomography, PET, allow physicians to see inside the body without a single incision. PET scans rely on antimatter, positrons released through radioactive decay. When these positrons meet electrons within the body, they annihilate each other, releasing gamma rays that reveal patterns of activity and early signs of disease. Quantum physics is not merely the foundation of matter, it has become a guardian of life. Quantum eyes, gazing toward distant galaxies. Let your eyelids grow heavy now. Allow your mind to drift beyond Earth, toward the vast edges of space. Quantum physics is also the tool that has granted us insight into the most profound mysteries of the cosmos. Using extraordinarily stable laser systems, the LIGO Observatory detected gravitational waves, faint ripples in space-time, caused by black holes colliding billions of years ago. For the first time, humanity learned not only to see the universe, but to listen to it. Quantum theory also helps us understand the birth of everything we see. In the earliest moments after the Big Bang, tiny quantum fluctuations were stretched by rapid cosmic expansion. These minute irregularities became the seeds from which galaxies, stars, and planets eventually formed. Even black holes, once thought eternal, are shaped by quantum law. Stephen Hawking showed that through quantum effects near their event horizons, black holes slowly emit energy, Hawking radiation, and may eventually fade away. Quantum mechanics is the language the universe used to write its opening chapter, and perhaps one day, its final line. The dawn of the quantum future. As night deepens, let your thoughts gently turn toward the future. There, powerful new machines are quietly coming to life. Quantum computers represent a leap beyond anything humanity has built before. Where classical computers process information as simple zeros and ones, quantum computers use qubits, units that can exist in multiple states at once and become linked through entanglement. These machines promise solutions to problems once thought unreachable, discovering new medicines, optimizing global energy systems, and probing questions at the edge of knowledge itself. We are also witnessing the early emergence of a quantum internet. Experiments using satellites such as Mykios have demonstrated quantum entanglement across distances exceeding 1,200 kilometers, enabling communication that cannot be secretly intercepted. Quantum teleportation, still limited to information and microscopic particles, has begun to reshape how we imagine space and time. You have seen how tiny particles, through their quiet and tireless dance, have woven together this vast and magnificent reality. From the phone resting near you to the black holes drifting in distant galaxies, everything is bound by invisible quantum threads. You are not lost, and you are not alone. You are the universe's way of becoming aware of itself, of seeing, of remembering, and of gently loving through consciousness. Are you still there, night travelers? As the murmurs of the daytime world gently recede, let us begin a quiet journey, away from noise and urgency, and toward one of the greatest confrontations in the history of human thought. Tonight, we will revisit the story of two towering rulers of the intellect, whose opposing visions opened the door to a new world, strange, unsettling, and profoundly beautiful. Settle into a comfortable position on your bed. Allow your shoulders to soften and feel a gentle warmth spreading from your chest to your fingertips. Breathe in slowly, inviting calm into your body, and exhale just as slowly, releasing the weight of the waking world. Welcome to the prelude, Two Rulers and a New World. The cracks in the clock universe. Our story begins long before this quiet night, near the end of the 19th century. At that time, humanity believed it had nearly completed its understanding of nature. The laws of Isaac Newton reigned supreme, forming what many called a clock universe, a cosmos as orderly as a finely crafted mechanism. If one knew the position and speed of an object, one could predict its future with certainty, from the path of the planets to the arc of a thrown stone. And yet, the first cracks appeared not in the heavens, but in something utterly ordinary, the incandescent light bulb. In the 1890s, as Germany surged forward through industrialization, engineers sought brighter and more efficient streetlights. What they encountered instead was a puzzle classical physics could not solve. Why did the color of heated filaments change? And why did the light refuse to grow ever bluer as temperatures increased? In the year 1900, a quiet and careful physicist named Max Planck stepped forward. To resolve what was known as the ultraviolet catastrophe, he proposed a radical idea. Energy is not released smoothly and continuously, but in tiny, discrete packets, quanta. Planck regarded this as a mere mathematical convenience, a temporary fix. He did not yet realize that he had placed the first stone of a revolution that would shake the foundations of reality itself. The first king, Albert Einstein and the particles of light. Breathe gently, evenly. Let your thoughts drift to a modest patent office in Bern, Switzerland, in the year 1905. There, a young clerk named Albert Einstein quietly nurtured ideas that would change the course of science. Einstein did not see Planck's quanta as a mathematical trick. He believed they revealed a deep truth about nature. To explain the photoelectric effect, how light striking a metal surface releases electrons, Einstein proposed a daring notion. Light itself comes in particles, later called photons. No longer gentle waves upon a lake, light became a stream of concentrated energy, arriving in precise bursts. This insight earned Einstein the Nobel Prize, yet it also plunged physics into a profound paradox. Light, it seemed, was both wave and particle. Einstein longed for a universe governed by clarity and reason, where every particle possessed a definite state, whether observed or not. He was a sovereign of logic, devoted to an objective reality that existed independently of human eyes. The second king, Niels Bohr, and the magical leaps. While Einstein reshaped our understanding of space, time, and light, another vision was forming in Copenhagen. Niels Bohr, curious, playful, and fearless in thought, approached physics with a mind open to contradiction. In 1913, Bohr applied quantum ideas to the atom itself. Electrons, he proposed, do not move freely like planets around the sun. Instead, they occupy fixed energy levels. When an electron absorbs energy, it makes a sudden leap, vanishing from one orbit and reappearing in another without crossing the space between. Pause with that image, dear traveler. Imagine stepping through a doorway in New York and finding yourself instantly in Paris, without the journey in between. Bohr did not concern himself with whether such a world felt intuitive. What mattered was that the mathematics worked and the colors of atomic light were explained. To Bohr, the atomic realm was not obliged to match human intuition. Nature, he believed, was not strange. It was simply deeper than our everyday experience. The Brussels meeting, a dance of uncertainty. Let your eyelids grow heavy. Now picture Brussels, October 1927, at the 5th Solvay Conference. Here, the greatest minds of the age gathered: Einstein, Bohr, Marie Curie, Planck, Heisenberg, Schrödinger. It was a moment when the future of physics hung in delicate balance. At this meeting, a younger generation of physicists, led by Bohr, presented a startling claim. At the heart of reality, certainty dissolves. According to Heisenberg's uncertainty principle, one can never know both the exact position and the exact motion of a particle at the same time. Even more unsettling, a particle does not possess definite properties until it is observed. Until then, it exists as a superposition, a quiet cloud of possibilities. Einstein was deeply troubled. He refused to accept a universe dependent on observation. "Do you really believe," he asked, "that the moon is not there when no one looks at it?" Each morning, he challenged Bohr anew, yet time and again, Bohr answered with unwavering resolve. Spooky action, the phantom link. The debate continued. In 1935, Einstein, along with Podolsky and Rosen, published a paper arguing that quantum mechanics must be incomplete. They highlighted a strange phenomenon Einstein mockingly called spooky action at a distance. Quantum entanglement suggests that two particles can become so deeply connected that their properties remain linked no matter how far apart they are. Change one here on Earth, and the other responds instantly, even if it lies in a distant galaxy. To Einstein, this violated the sacred limit of light speed. He imagined hidden variables, like gloves already paired before being separated. Bohr, however, maintained that properties come into existence only through measurement. History would later side with Bohr. Experiments confirmed entanglement as a fundamental feature of nature, revealing a universe more subtle and interconnected than Einstein ever wished to accept. You have now glimpsed two monarchs of thought, united by devotion to truth and divided by vision. Einstein revealed the deep unity of light, mass, space, and time. Bohr led us into the elusive heart of the atom. Their disagreement was not a failure, but a gift, one that gave rise to the technologies surrounding you tonight, from lasers and smartphones to the quantum machines of tomorrow. And now, allow peace to settle fully. The universe has labored for billions of years so that a small part of itself, you, may rest here, breathing quietly, aware of its beauty. Do not fear uncertainty. It is what holds your atoms together and allows the sun to warm this fragile world. Relax completely. Let your eyelids fall. Drift gently into sleep beneath the soft, silent galaxies. The universe was born from a profound silence, and tonight, it keeps watch over your dreams with infinite care. Night travelers, let us rest our eyes upon this warm, flickering fire. For a moment, we release our minds from the urgency of daily life and step into a battle without weapons, yet one powerful enough to shake the very foundations of what we call truth. This is a quiet war of ideas fought between two towering intellects, Albert Einstein and Niels Bohr. Welcome to this chapter, The War of Ideas. God doesn't play dice. Allow your breathing to become slow and steady. Let each word drift gently toward you as the story of two great friends and lifelong rivals guides you toward rest beneath the distant, shimmering galaxies. When the clockwork universe began to falter. Dear night travelers, imagine we are gently turning back the pages of time, returning to the early years of the 20th century. Before then, the universe appeared calm, orderly, and reassuringly predictable. Isaac Newton had taught humanity to see the cosmos as a vast clockwork. If one knew the position and velocity of an object, its future could be calculated with perfect certainty. Cause led unfailingly to effect. Reality existed, solid and complete, whether anyone observed it or not. But that elegant picture began to fracture when scientists dared to look inward, deep into the heart of matter itself. Within the tiny realm of atoms, the familiar rules no longer held. And onto this uncertain stage stepped two remarkable figures, Albert Einstein and Niels Bohr, destined to guide humanity into a world stranger than imagination had ever allowed. Einstein, often called the godfather of quantum physics, made a daring leap in 1905 when he proposed that light was not merely a wave, but also a particle, later named the photon. Yet despite this bold insight, he longed for a universe governed by order, where every particle followed a predetermined path. Bohr, by contrast, offered a vision that was both radical and unsettling. In his atomic model, electrons did not glide smoothly through space. Instead, they performed sudden quantum leaps, vanishing from one orbit and appearing in another without crossing the distance between. To Bohr, the microscopic world was not precise and fixed, but inherently uncertain. Together, these two explorers opened the door to the quantum realm. What they discovered beyond it, however, transformed companionship into a decades-long struggle over the nature of reality itself. Solvay, 1927. A symphony of uncertainty. Breathe slowly, softly. Now picture Brussels, October 1927, at the 5th Solvay Conference. Before you stands a historic photograph. Einstein seated in the front row, thoughtful and reserved. Bohr just behind him, eyes bright with conviction. Gathered around them are the greatest scientific minds of the age, united to confront a theory that was unsettling everything humanity thought it knew. Here, Bohr and younger physicists such as Werner Heisenberg introduced what became known as the Copenhagen interpretation. They claimed that a particle, an electron for instance, does not possess a definite position until it is observed. Before measurement, it exists in a superposition, a quiet overlap of all possible states at once. Heisenberg's uncertainty principle further revealed that one can never precisely know both a particle's position and its motion at the same time. Einstein was deeply disturbed. He could not accept a universe ruled by chance. To him, probability signaled a failure of understanding, not a fundamental truth. He voiced his frustration in words that would echo through history. God doesn't play dice with the universe. Bohr, calm yet resolute, replied gently, Albert, stop telling God what to do with his dice. The deeper question, is the moon there? Let your eyelids grow heavy. Allow your thoughts to drift into the late-night discussions that unfolded at the Metropole Hotel. These were not debates over equations alone, but over the essence of existence. Einstein held firmly to realism. He believed that the universe exists independently of us. He posed his famous challenge. Do you really believe the moon is not there when no one looks at it? For him, physics was meant to reveal hidden certainty, not to surrender to ambiguity. Bohr saw the matter differently. He argued that observer and observed cannot be separated. Reality, he insisted, becomes meaningful only through measurement. His principle of complementarity explained how an object could appear as a wave or a particle, depending on how it is examined. Their disagreement forced humanity to confront a profound question. Is truth something waiting to be uncovered, or something that emerges through our interaction with the universe? EPR and spooky action, Einstein's final challenge. In 1935, now settled in Princeton, Einstein continued to wrestle with quantum theory. Alongside Rosen and Podolsky, he published what became known as the EPR paper, seeking to expose a fatal flaw in Bohr's interpretation. They focused on a strange phenomenon later called quantum entanglement. According to quantum mechanics, two particles could become so deeply linked that measuring one instantly determines the state of the other, even if they are separated by vast distances. Einstein dismissed this as spooky action at a distance, arguing that it violated the speed limit imposed by relativity. He offered a more comforting analogy, a pair of gloves sealed into two boxes. If one box is opened in New York and reveals a left glove, the other, opened at the South Pole, must contain the right glove. No mystery, no instant influence. The properties were set from the beginning. To Einstein, quantum mechanics was incomplete, missing hidden variables that would restore order. Bohr, after many sleepless nights, responded with a subtle yet firm defense. The entangled particles, he argued, were not separate objects at all, but parts of a single, indivisible whole. Their connection transcended classical notions of space and separation. Bell's verdict: when experiments speak. Night travelers, our fire has now burned down to glowing embers, each one like a photon waiting to tell its final story. For decades, this debate was considered philosophical. Then, in 1964, a physicist named John Bell transformed the argument into a testable question. Bell derived a mathematical inequality that could distinguish between Einstein's hidden variables and Bohr's quantum reality. If Einstein were correct, measurements would obey certain limits. If Bohr were right, nature would violate them. Through experiments conducted by John Clauser, Alain Aspect, and later Anton Zeilinger, the verdict became undeniable. The universe sided with Bohr. Entanglement was real. The quantum world was not a clockwork machine, but a delicate web of possibilities and, although Einstein did not succeed in overturning quantum mechanics, his relentless questioning drove science forward. Because of this struggle, we now have lasers, transistors, and stand at the threshold of quantum computing. And we learn something quietly profound. Though we are small inhabitants of a faint blue dot, the human mind can reach across billions of light years to understand the rhythm of creation itself. Are you still there, night travelers? If you have already drifted into sleep, that is wonderful. And if you are still awake, stay with me a little longer. Tonight, we will not speak only of tiny particles hidden from view, but of how those particles become the eyes that allow us to gaze into the deepest sky. Welcome to this chapter. Quantum eyes gazing at the sky. Let your breath be light and even, and listen quietly to the love song of quantum physics, a song that has forever changed astronomy, revealing the secrets of black holes and the strangest stars in the universe. Introduction: when the smallest reality governs the greatest things. Dear night travelers, for thousands of years, humanity looked up at the heavens and saw a picture of calm order and unshakable certainty. In Isaac Newton's vision, the universe was a magnificent clockwork, where planets and stars followed precise paths that could be calculated millions of years into the future. Yet as scientists began to explore the smallest layers of reality, atoms and subatomic particles, they discovered something astonishing. The foundation of that colossal cosmic machine was not rigid and mechanical, but woven from laws that were subtle, elusive, and deeply strange. Quantum physics is not a theory removed from reality. It is the source code of reality itself. Though its effects reveal themselves most clearly on microscopic scales, their influence reaches far beyond, governing how stars burn and how gravity's most fearsome creations behave. Without quantum mechanics, the night sky above you would be dark and lifeless. Modern astronomy has become a kind of quantum archaeology, using the behavior of tiny particles to reconstruct the history of the grandest objects in existence. Quantum eyes and the revolution in astronomy. For centuries, astronomy relied on visible light alone. But quantum physics taught us a deeper truth. Light is not merely a wave, but also a stream of energetic particles known as photons. This realization opened an entirely new window onto the universe. Every atom within a distant star leaves a precise and unmistakable signature in the light it emits, a spectral fingerprint. When electrons shift between energy levels, they absorb or release photons of exact energies. By reading these spectral lines, astronomers can determine the composition, temperature, and motion of stars thousands of light years away, without ever leaving Earth. Quantum physics also lies at the heart of our most advanced instruments. The James Webb Space Telescope, with its exquisitely sensitive infrared vision, peers through cosmic dust to observe the universe's earliest light, the moment when the first stars ignited. Every detector, every transistor guiding its signals, is a triumph of quantum mechanics. We now live in a true quantum age, where understanding the smallest particles allows us to detect even the faintest tremors in space-time itself. Gravitational waves rippling through the cosmos. The miracle of the quantum tunnel. Why the sun shines. Breathe slowly, deeply. Imagine yourself at the heart of the sun, where temperatures soar into the tens of millions of degrees. There, protons race toward one another at extraordinary speeds. According to classical physics, their positive charges should repel so strongly that fusion would be impossible. By those rules alone, the sun should never have ignited, and life on Earth would never have begun. Yet the sun shines, and it shines steadily, thanks to a quantum miracle known as tunneling. In the quantum world, particles are not solid beads, but waves of probability. A proton does not occupy a single fixed location. Its presence spreads and shimmers. Picture a traveler facing a steep mountain they lack the strength to climb. In classical terms, the journey ends there. But a proton, in a fleeting instant, can slip through the energy barrier as if it were a ghost, appearing on the other side without ever crossing the peak. This tunneling allows protons to fuse into helium, releasing the energy that warms our world. The gentle ambiguity of quantum mechanics is, quite literally, the engine of the sun, and the quiet guardian of our existence. Black hole, monsters, and Hawking's whisper. Let your eyelids grow heavy. Now drift with me to the edge of a black hole, where gravity bends space and time beyond recognition. For many years, black holes were thought to be absolute endings, places where matter and information vanished forever. In 1974, Stephen Hawking offered a softer, more unsettling truth. Quantum mechanics revealed that empty space is never truly empty. It seethes with fleeting particle pairs that appear and vanish almost instantly. Near a black hole's event horizon, one particle may fall inward while its partner escapes, unable to reunite. To a distant observer, this escape appears as a faint glow, now known as Hawking radiation. Through this whisper of radiation, a black hole slowly loses mass and, over unimaginably long spans of time, can evaporate completely. Even these giants are not immune to quantum law. This insight gave rise to the information paradox. Does information truly vanish inside a black hole, or is it preserved in subtle quantum imprints upon its surface? Some theories, such as the fuzzball concept in string theory, suggest that black holes may be vast tangles of vibrating quantum threads, ensuring that nothing is ever truly lost. Neutron stars and pulsars, extreme quantum laboratories. Beyond black holes, we encounter other extraordinary remnants, neutron stars. These are the collapsed cores of massive stars, so dense that a single teaspoon of their material would outweigh a mountain on Earth. Here, atoms are crushed beyond recognition, forcing electrons and protons to merge into neutrons. What prevents these stars from collapsing entirely into black holes? The answer lies in quantum degeneracy pressure. According to the Pauli exclusion principle, certain particles stubbornly refuse to occupy the same state in the same place. This quantum resistance generates a force strong enough to counter gravity's relentless pull. Within neutron stars, matter enters exotic states rarely seen elsewhere: superfluidity and superconductivity. Neutrons can flow without resistance, and this behavior explains sudden changes in a pulsar's rotation, known as glitches, caused by interactions between the rigid crust and the superfluid core. Each pulsar, sending its steady rhythmic signal across space, becomes a colossal quantum clock, turning silently in the darkness. You have just glimpsed a universe that is not only vast in scale, but also governed by the most delicate and elusive laws of the quantum world. From this journey, one quiet truth emerges. Physical smallness is not weakness. It is evidence of the greatness of consciousness. That we can use photons, electron transitions, and the tunneling effect to unveil the secrets of black holes and distant stars may be the most astonishing miracle of existence itself. Night travelers, settle gently into your soft bed. Let your shoulders release their weight and feel a quiet warmth spreading from your chest to your fingertips. Take a deep breath, drawing calm into your body. And exhale slowly, letting the concerns of the waking world drift away. Tonight, we open a new chapter together, decoding the source code of the universe. Awakened stardust and the microscopic symphony. Dear travelers, before we descend into equations and abstractions, remember this comforting truth. You are children of the stars. Every atom that forms your being, the iron flowing through your blood, the calcium shaping your bones, the oxygen carried in each gentle breath, was forged in the blazing hearts of massive stars that lived and died billions of years ago. We are, in the most literal sense, awakened stardust. After 13.8 billion years of cosmic wandering, a portion of the universe has become conscious, becoming you, becoming me, quietly reflecting upon itself. But what governs these atoms? What prevents them from collapsing and allows them to assemble into life? The answer lies in quantum physics, the science of the universe's smallest inhabitants, atoms, light, and subatomic particles. Though it studies the tiniest scales, quantum physics reaches far beyond them, determining how stars shine and how the vast architecture of the cosmos takes shape. When nothing is not truly empty, breathe softly, evenly. Imagine drifting through intergalactic space, surrounded by darkness and near-perfect silence. Classical physics once taught us that a vacuum is complete emptiness. Quantum physics tells a far more subtle story. According to the uncertainty principle, even absolute emptiness is restless. Space itself seethes with quantum fluctuations, where pairs of virtual particles and antiparticles briefly appear, dance together for an instant, and vanish again. In this sense, the universe may have borrowed energy from nothingness itself, emerging through a quantum tunneling event. Picture the universe as an athlete facing an immense energy barrier. Classical laws say the barrier is impossible to cross, yet quantum mechanics allows a faint possibility, a momentary passage through the wall itself. Physicists such as Alexander Vilenkin suggest that our entire cosmos may have tunneled from a state of no space and no time into the hot, dense beginning we call the Big Bang. The quiet imbalance, matter and antimatter. Let your eyelids grow heavy. Drift back to an instant just 10 to the power of minus 43 seconds after the Big Bang, during the Planck era. The universe is a searing ocean of energy where all fundamental forces are unified into one. As space expands and cools, a subtle but decisive event unfolds, baryogenesis. In theory, the Big Bang should have produced equal amounts of matter and antimatter. Had that balance been perfect, everything would have annihilated itself, leaving only light behind. Yet quantum physics reveals a minute asymmetry, a violation so small that only one extra particle remained for every 10 billion annihilations. Every galaxy, every star, and every living being tonight exists because of that tiny imbalance. We are the quiet survivors of a cosmic accident, a whisper of difference that shaped all existence. The solar engine and the miracle of passage. Feel the gentle warmth around you, like sunlight on a calm afternoon. The sun that sustains life shines because of quantum law. At its core, protons rush toward one another at extraordinary speeds. Classical physics insists they should never fuse. Their electrical repulsion is too strong. Were Newton's laws alone in command, the sun would fade instantly. But quantum tunneling intervenes. Protons can momentarily bypass the barrier, combining into helium and releasing the energy that bathes Earth in light. Quantum physics is not confined to laboratories or equations. It is the steady heartbeat of the sun warming you tonight. Black holes and Hawking's gentle murmur. Let your thoughts drift to the edge of a black hole, where gravity bends reality beyond recognition. Once thought to be absolute ends, black holes revealed a quieter truth in 1974, when Stephen Hawking applied quantum mechanics to their edges. Near the event horizon, virtual particles continually appear. Occasionally, one falls inward while the other escapes, becoming real. To a distant observer, this escape appears as Hawking radiation, a faint whisper from the darkest objects in the universe. Over unimaginable spans of time, this radiation allows black holes to evaporate. New theories even suggest that black holes may not be singular points at all, but fuzzballs, vast tangles of quantum threads where information is preserved in ways we are only beginning to grasp. The cosmic web, uncertainty made visible. Breathe deeply. The immense structure of the universe, galaxies and superclusters, was born from tiny quantum fluctuations. In the earliest moments after the Big Bang, these fluctuations were stretched across space during cosmic inflation, becoming regions slightly denser than their surroundings. Over billions of years, gravity shaped these faint irregularities into the cosmic web we observe today. When you gaze at maps of the universe, you are witnessing quantum uncertainty magnified to galactic scales, a frozen echo of the universe's first breath. Is the universe written in mathematics? As night deepens, consider a daring thought proposed by physicist Max Tegmark. Perhaps at its deepest level, reality is not physical at all, but mathematical. Strip an apple down to its most fundamental level, and qualities like color or scent vanish. What remains are numbers: mass, charge, spin. These numbers may be the lines of code that govern existence itself. If the universe is a vast mathematical structure, then quantum laws are its operating system, quietly ensuring stability, order, and the emergence of life. You need not fear chaos. This source code has been refined with extraordinary care, allowing consciousness to arise and wonder. Though we rest on a single faint blue dot, our awareness reaches across billions of light years, listening to the gentle rhythm of creation itself. Find a comfortable position on your soft bed. Let your shoulders release their weight completely, and feel a gentle warmth spreading from your chest to your fingertips. Take a slow, deep breath, inviting calm into your body. Then exhale quietly, letting the concerns of everyday life drift away. Allow your mind to become light, like grains of cosmic dust floating through the eternal glow of the stars. You may have heard the phrase, the quantum realm, in popular films such as Avengers or Ant-Man. On the cinema screen, it is portrayed as a glowing, otherworldly dimension where humans shrink without limit, bend time, or reshape reality in an instant. Yet, dear traveler, the true quantum realm is far more subtle and far more astonishing than any spectacle imagined by film. It is not a place of fantasy. It is the unseen foundation governing every atom in your body, every shining star above you, and the entire vast universe itself. To understand it, we must gently release our everyday logic and step into a realm where certainty softens into probability. Before quantum physics, humanity understood the universe through what we now call Newtonian classical physics. It was a precise mechanical cosmos, a universe that ticked like a perfectly wound clock. If you threw a stone with a known force and angle, you could predict exactly where it would land. Time flowed evenly for all, and space was a quiet stage awaiting its actors. Then, at the close of the 19th century, something unexpectedly ordinary shattered this certainty: the light bulb. Engineers could not explain why the color of light changed as the filament heated. Classical physics collapsed under what became known as the ultraviolet catastrophe, a small crack that would soon open into a revolution. In 1900, a reserved physicist named Max Planck offered a daring solution. He proposed that energy does not flow smoothly, like water from a stream, but arrives in tiny, indivisible packets. He called these packets quanta, from a Latin word meaning how much. Planck himself believed this idea was merely a mathematical convenience. Yet, unknowingly, he had opened the door to a new understanding of reality, one in which nature moves not in smooth lines, but in discrete jumps. 5 years later, Albert Einstein took the idea further. In explaining the photoelectric effect, he proposed that light itself behaves as a stream of particles, later called photons. Light, long understood as a wave, revealed a second identity. This wave-particle duality became the first clear sign that the quantum world does not obey the rules of everyday experience. As we descend into the microscopic realm, all intuitive notions of solidity dissolve. If a soccer ball were expanded to the size of the Earth, only then would the atoms within become visible. Yet inside those atoms, electrons do not travel like tiny planets around a sun. The famous double-slit experiment revealed something extraordinary. A single particle can pass through two paths at once, interfering with itself like a wave. Only when observed does it appear to choose a definite position. This is known as quantum superposition. Imagine a coin spinning on a table, neither heads nor tails, but a blur of both. In the quantum world, particles exist as possibilities rather than certainties, until observation brings one outcome into view. From this idea came Schrödinger's thought experiment of the cat, neither alive nor dead until the box is opened. Here, certainty gives way to probability. Werner Heisenberg showed that there is a fundamental limit to knowledge. One cannot know both the exact position and exact motion of a particle at the same time. The more precisely you know where it is, the less certain you are of where it is going. It is as if mystery is woven directly into the fabric of existence itself. This uncertainty sparked one of the greatest intellectual debates in history. Albert Einstein, guided by reason, rejected a universe ruled by chance. God does not play dice, he insisted. Niels Bohr responded with calm resolve, arguing that reality takes shape through observation and interaction. "Do not tell God what to do," he replied. In attempting to challenge Bohr, Einstein highlighted what he called spooky action at a distance, quantum entanglement. Two particles, once linked, remain connected regardless of distance. Change one here, and the other responds instantly, even across galaxies. Einstein found this impossible, yet decades later, experiments confirmed it. The universe is not a collection of separate parts, but a single, deeply connected whole. Why, you may wonder, have we pursued these strange ideas for so long? Because quantum physics governs everything around you. Without it, atoms would collapse, matter would unravel, and even the bed beneath you would not exist. Every modern technology, from transistors and lasers to fiber optic communication and GPS, relies on quantum laws. Quantum mechanics is not distant or abstract. It is the quiet architect of daily life. Beyond technology, quantum physics illuminates the deepest mysteries of the cosmos. The sun shines because of quantum tunneling, allowing particles to overcome barriers they should never cross. Black holes, once thought to be eternal prisons, slowly fade through Hawking radiation. Even the vast structure of galaxies traces its origins to tiny quantum fluctuations in the early universe. Looking ahead, quantum science may one day allow humanity to solve problems once thought impossible. Quantum computers, teleportation of information, and new forms of discovery are already emerging. Though many questions remain, the boundary between the impossible and the achievable grows ever thinner. And now, dear traveler, the night draws gently to a close. Like fading embers, our thoughts settle into quiet light. You have seen how the smallest particles, through their subtle dance, have shaped a universe of immense beauty. You are not insignificant in this vastness. You are awakened stardust. Every atom within you was forged in ancient stars. guided by the same quantum laws that govern galaxies and time itself. The universe has spent 13.8 billion years preparing for this moment, so that a part of it, you, can rest here, breathing softly, feeling its presence. Let go of uncertainty. It is what holds the atoms together and keeps the stars in their paths. Relax completely, like gentle ribbons of the Milky Way stretching across the sky. The universe began in silence, and tonight, it watches over your sleep with quiet care. Sleep well, night travelers.